Here we're going to learn how to perform calculations with vectors. But before we do that, let's introduce some new terms. So let's say that this is your coordinate system, positive x-axis, positive y-axis, and let's say that this vector here points in this direction, vector v. So you can get from the back of the vector, which is called the tail, to the front of the vector, which is called the tip. You can get there in two ways. You can just walk directly from the tail of the vector to the tip, or you can break it down into two steps. You can walk horizontally by this distance here, and then you can walk up vertically by this distance here. So the horizontal motion, we're going to say that this is the motion along the x-axis, and we're going to call that the x component, Vx. So Vx is going to represent the x component of a vector. And when you walk upwards in a y direction, since you're going in the y direction, we're going to call that the y component of the vector, Vy. So Vy represents the y component of a vector. So now let's do more practice with the x and the y components. So let's just refresh this. Let's look at this vector here. So now the ax, that represents the x component of vector A, which is 10, and the y component is also 10. So if I just put the coordinate system there, you can see there, you have to walk horizontally by 10 and walk vertically by 10 to start at the back of the arrow and end up at the tip of the arrow. And let's say that you have this vector here. So here, to start from the back of the vector and end at the tip, you have to walk horizontally by 30 units. So the x component is 30, and you have to walk up vertically by 15 units. Let's say that you have another vector. Let's say that this is this one here. So to start at the tail of the vector and at the tip, you have to walk horizontally but backwards by 26 units. So the x component is minus 26, and you have to walk up in the positive y direction by 5 units. So ay is positive 5. And over here, to get to the tip of the vector, you start at the origin, you have to walk backwards by 19 units. So the x component is negative 19. And you have to walk down 9 units. So the y component is negative 9. And let's say this is your final vector. So to get to the tip of this vector, you have to walk forwards by 15 units. So the x component is 15. And you have to walk down by 10 units. So the y component is minus 10. So let's now get our first formula. So let's say that, so here, let's draw the coordinate system again. And now we're going to include everything that we learned so far. Your positive x-axis, your positive y-axis. And let's say that this is your vector here, vector v. And its direction, you always measure it relative to the positive x-axis. So start at the tail. I recommend that you draw an x-axis like this. And you're going to rotate counterclockwise until you hit the vector. So let's go back to the computer simulation to put all this together. So the first picture that we had was like this. You had the length of the vector and you had the direction. That's what I just showed you. But we can interpret this in another way in terms of the components. So the same vector, you can look at it as, in order to get from the tip of vector, in order to get to the tip of the vector, you have to walk across by 15 and up by 15. And for example, this one here, you have to walk back by 17 units and up by 16 units. And this vector here, to get to the tip of the vector, you have to walk forwards by 10 units, forward by 14 units and down by 10 units. But in each case, you notice that we're always making a right triangle. So let's go ahead and represent our vector in terms of a right triangle. So here, instead of writing this vector as an arrow in a direction, but let's always do a coordinate system, positive x-axis, positive y-axis. This same vector v, you can write it as a right triangle, where the vector itself represents the hypotenuse, and the bottom leg, the horizontal leg of the right triangle, represents the x component of the vector, vx, and the vertical component of the right triangle represents the y component of the vector vy. Do that in a different color. So the y component of the vector represents the vertical part, which is vy. And the angle is still going to be this one over here. So in order to get a formula for the x and y components, let's look at an illusion. So here in this picture, you see a hand, and it looks like it's grabbing a cloud. Clearly, your hand isn't as big as a cloud, so let's see how this effect works. And it's in terms of ratios. So let's say that this is the ground here. And this is your hand. Well, yeah, let's just say that this is your hand here. And the reason why your eye appears to see your hand being the same size as the cloud is that, so let me try to draw this a little bit better here. From your eye, there's a triangle where your eye is at one vertex that passes just above the top of your hand and then just below the bottom of your hand. And that triangle keeps on going outwards into space. And the way that this illusion works is that the cloud happens to line up so that the top of the cloud, even though it's much bigger in your hand, bigger than your hand, and the bottom of the cloud fit within that same triangle. So because of that, it appears to your eye that the size of your hand is the same as the size of your eye. But even what's really the same is not the size, but the ratio of the height of your hand to, for example, the bottom of this triangle here is the same as, for the cloud is the same. So the ratio of the height of the cloud to the bottom of this triangle here is the same. So we're going to use ratios when we discuss the triangular parts of a vector. Let's redraw our vector. So you have your positive x-axis, and you have your positive y-axis. And let's say that the vector points in this direction. So a new way to get to the tip of the vector is to walk horizontally by a distance vx, and then to walk up vertically by a distance vy. And we're also going to have the angle here measured relative to the positive x-axis. And also, the length of the vector represents the hypotenuse of this right triangle. So we're going to use ratios to describe these terms. All right, so the first ratio that we're going to define is going to be the ratio of the vertical part of the motion to the hypotenuse. So we're going to say that the ratio of the vertical part of the motion to the hypotenuse, we're going to call that the sine of the angle. And the next ratio, we're going to say that the ratio of the horizontal part of the motion to the hypotenuse, we're going to call that the cosine of the angle. And so now we can rewrite these. Well, we can say that the y component of the motion is going to be the magnitude or the hypotenuse of the vector multiplied by the sine of the angle of the vector. And using this equation, you can solve for the x component of the vector. So Vx is going to be the magnitude of the vector v multiplied by the cosine of the angle. And these are two important formulas. These are going to be used for word problems where you're given the magnitude v and the direction theta, and you want to find the x component and the y component.